A differential equation is any equation that contains a derivative. And ordinary differential equations, those are the ones that we're actually concerned with in this class. Because we talked about PDEs. They're just a little bit too hard to analyze or do anything with. They're definitely super duper important, but that's normally saved for, I don't know, mostly grad school stuff. So today my plan is to learn how to classify ODEs and learn a bunch of vocabulary words that describe ODEs. The first thing is the order. The order of an ODE is the highest order of the derivative involved. So like if you've got a first derivative and that's it, that would be a first order ODE. If you've got a second derivative present, then it becomes a second order ODE because of that. And then if you have a third derivative present, it would be a third order ODE and so on. So the order tells you what's the biggest derivative that you have to deal with. The next word is linear. And this is a really hard one to grasp, I think. We say that an ODE is linear if it's linear in the dependent variable and the derivatives of the dependent variable. As for the independent variable, like the t, it can be whatever it wants to, right? Like it can be as non-linear as you want to be for your t variable. It only matters that you have a linear combination of the dependent variable and its derivatives. So, like in exercise 1 right here, where it says dy dt is equal to the square root of t plus y, would you say that's a linear or non-linear ODE? Linear. So the square root of t is a non-linear function of t. We don't care about that because t is my independent variable. I only really care that my differential equation is linear in terms of the dependent variable. Nobody cares what happens to the independent variable. Okay. Next one, t plus square root of y. Yeah, that's non-linear. What about sine of y double prime minus y prime cubed plus cosine of y? Equals 0. This one is non-linear. Because all these functions, sine, cube, cosine, all those are non-linear functions, and y is my dependent variable. So if it's a non-linear function of the dependent variable or its derivatives, then it's a non-linear function. Oh, non-linear ODE, I mean. Now look at the next equation, the one on the bottom here. Is that linear or non-linear? This one is a linear ODE. Because even though I have the same nonlinear functions, I still have sine, I still have t cubed, I still have cosine of t. even though they're all nonlinear functions, it's only affecting my independent variable. And nobody cares if your independent variable has crazy stuff going on. We're really only worried that it's linear in terms of the dependent variable and its derivatives. Okay, do you guys feel like you understand what makes this linear? It's only linear if you can have, crazy functions of t times just y and just y prime and just y double prime and so on. Okay. First order ODE is separable if it can be written in the following form. We write f of y times y prime is equal to g of t. So this is separable because we have separated the y's and the t's. So the left side of my equation has only y's and the right side of my equation has only t's. And it has to be written in that form. Okay, so what about this? Y prime equals r times y, is that separable? This is separable because I can write it like 1 divided by y times y prime equals r. So when I compare it to the separable form, I say, well, f of y is 1 divided by y, and g of t is this constant r. So yeah, it's separable. In the next one, I've got y prime equals t plus y. Is that one separable?
I would say yes, because you can move the y to the other side.
Okay. So I could write it like negative y plus y prime equals t. But this is not separable. Because I have to be able to multiply some function of y times y prime. But I don't have some function of y times y prime. I have some function of y plus y prime. And so this is technically not separable. So it's not enough to just move the y's to the left side and just move the t's to the right side. You really have to have a function of only y times y prime, and on the right side a function of only t. So that's a little tricky. What about y prime equals y times 1 minus y? Is that separable? Yep. I can write 1 over y times 1 minus y times y prime equals 1. So that's separable. What about y prime equals ty plus y? Is that separable? What if I divide both sides by y? That is a function of only y times y prime equal to a function of only t. So that is separable. Okay, what about the next one? We got y prime equals t plus y squared minus 2ty. So I could rewrite this one like negative y squared plus y prime equals t squared. Is that separable? No, not separable. Because for it to really be separable, we would need a function of only y times y prime, not plus y prime. What about y prime equals e to the ty? Is that separable? Connor, I see you nodding your head. How do I separate this so it looks like a function of only y times y prime equals a function of only t?
Take the natural log of both sides.
Natural log of both sides?
That way, yeah, so you can put 2y and then divide by 1 over y.
Divided by y on both sides? Yeah, but then we don't know how to get rid of the natural log again, right? And so to make it look like this form right here, we're not going to be able to do it, right? We don't have it just a function of y times y prime on the left. It's close, but not separable. Okay. An ODE is autonomous if it may be written without explicitly using the independent variable. This is much easier to figure out. Is this one autonomous? R is a constant. I should say that R is constant. Then yeah. So this is autonomous. What about y prime equals y times 1 minus y? Is that autonomous? Yes, that's also autonomous. What about y prime equals ty plus y? No, not autonomous. What about the last one? That's a trick question. Because if you simplify it, but yeah, you got the idea. It's like if you see the t, then it's not autonomous. If there are no independent variables, then it is autonomous. So let's talk about your handout now, because everybody should have a handout that looks like this. This is what we are going to be focused on in this class for the first test and the second test and the third test. For the fourth test, we're going to go off and do other things. But the main idea for our first test in this class is we're going to take first order ODEs and we are going to decide is it linear or nonlinear. And if it's linear, we're going to figure out if it's separable or not separable. And if it's separable, we are going to solve it using a certain strategy that I called separate and integrate. If it's not separable, but it's still linear, we're going to solve it using a strategy called using an integrating factor. If it's first order and nonlinear, then there's a bunch of other categories that it could fall into. Like maybe it's separable, maybe it's homogeneous, maybe it's exact, maybe it's not exact, but you can make it exact. Maybe it's Bernoulli, and if it falls into one of these categories, we're going to have a different strategy for solving the equation. There are some first order nonlinear equations that you can't solve by hand, okay? Just like with certain antiderivatives, you can't write down a closed form solution to them. So that definitely exists, and that's why our frowny face is there, is because there's lots of ODEs that cannot be solved. But we are going to categorize and solve the ones that we can. For our second test in this class, we're going to take a look at second order ODEs that are linear and have constant coefficients, and we are going to solve them using a characteristic polynomial and variation of parameters. Those are just strategies we're going to learn later on. For our third test in this class, we're going to take a look at second order linear ODEs that have constant coefficients that are not homogeneous that we'll solve with Laplace transforms, and then we'll take a look at second order linear non-constant coefficient ODEs that we'll solve with power series solutions. And if you ever see a second order nonlinear ODE, that's not for this class. We're just not going to solve that here. Not going to think about it. One little warning, though, is that the word homogeneous appears twice or even 3 times. But this is not the same as this. Okay? In the first one, where you're looking at a first order nonlinear homogeneous ODE, the word homogeneous means something different. And when you're looking at a second order linear homogeneous ODE, the word homogeneous means something completely different. So we won't talk about that too much today, but in the future, just be aware that homogeneous is exactly the same word with exactly the same spelling and the same pronunciation, but it means 2 very different things, depending on context. Oh, I guess we will talk about it today. I put this in my notes. What it means to be a first order nonlinear homogeneous ODE is one that can be written like this. You've got y prime equal to a function of y divided by x. So you can rewrite the ODE in such a way that every single time y appears, it's divided by x. And every single time the x appears, it's y divided by x. If that's the case, we call it homogeneous for a first order nonlinear ODE. A second order homogeneous ODE is one that can be written like this. And notice that it's linear, so the y and the y prime and the y double prime only appear as a linear combination with, possibly nonlinear functions of t here as the coefficients. But what makes this homogeneous is that the right-hand side is just 0. So for a second order linear ODE, the right-hand side is 0, and that's what makes it homogeneous. For a first order nonlinear ODE, what makes it homogeneous is having this y over x part. 2 different definitions, depending on context. Okay. Exercise 4 says classify each of the following ODEs using the flowchart. So the first thing we're going to do when we see exercise 4 is we're going to ask, is this first order or second order? Second, because I see a second derivative there, so second order. And then I ask, is it linear or nonlinear? Linear. And what's the next thing? Is it constant coefficients or non-constant coefficients? My coefficients here are going to be t squared, and then t, and then 2. Those are what we call the coefficients. It's the stuff that multiplies the y's and the y primes. So we would call these non-constant coefficients. Because t and t squared aren't constants. And then, is this homogeneous or non-homogeneous? Remember, what makes a second order linear ODE homogeneous is that the right-hand side is 0, but this time the right-hand side is not 0. So this is non-homogeneous. So if you were trying to describe this ODE to somebody, you would have to tell them this is a second order, linear, non-constant coefficient, non-homogeneous ODE. And that way they would know how to solve it. They would say, oh yeah, you could solve that using a power series solution. Which we'll do later this semester, but for right now we're just trying to follow the flowchart, second order, linear, non-constant, non-homogeneous series solution. Okay, the next one. I've got y prime equals 5 minus y. Is this first order or second order? First. Is it linear or nonlinear? Linear. And if it's first order linear, the next thing we ask is it separable or not separable? It is separable. Because to write it as separable, I would have to write 1 divided by 5 minus y times y prime equals 1. But that's a function of only y times y prime. So it's first order linear separable. Is it autonomous? Yes. It is autonomous. Autonomous just means you don't see the letter T anywhere. And here's a little hint. Any autonomous ODE has to be separable. If you see a first order ODE and you don't see any T's, then it's definitely separable every time. Autonomous implies separable. Separable doesn't have to be autonomous, but autonomous has to be separable. So anyways, if I was trying to fully describe this to somebody, I would say this is a first order linear separable autonomous ODE. Or I could just say first order linear autonomous, because autonomous implies that it has to be separable. Okay. Next, I've got t squared y double prime plus 4t y prime plus 2y equals 0. Is this first order or second order? Second order. Is it linear or nonlinear? Linear. Is it constant coefficients or non-constant coefficients? Non-constant. And is it homogeneous or non-homogeneous? Homogeneous. Next, y prime equals square root of ty. Is it first order or second order? First. Is it linear or nonlinear? Linear. Is it separable or not separable? Is it autonomous or not autonomous? Okay, y prime equals y times 1 minus y. Is that first order or second order? First. Is it linear or nonlinear? What did you say?
Linear. Not. Squared. Yeah.
Yeah, I'd have y minus y squared. That's not linear. First order nonlinear. Is it separable? I think we said earlier, in fact, that this one was separable. Is it autonomous or not autonomous? No t's, so it's autonomous. There we go. Y prime equals t squared y cube. Is that first order or second order? First order. Is it linear or nonlinear? Is it separable or not separable? Separable. Is it autonomous or not autonomous? Next one, 1 minus y times y prime plus y equals 0. Is that first order or second order? Is it linear or nonlinear? Nonlinear. So this is nonlinear because I have y times y prime, and you're not allowed to multiply the y times any of its derivatives. So y times y prime, that doesn't fly, that's nonlinear. First order, nonlinear, is it separable or not separable? It's separable because it's autonomous, right? Every autonomous equation has to be separable. So you could separate it by subtracting y from both sides, dividing both sides by 1 minus y, and then you get y prime equals negative y divided by 1 minus y, and then you multiply both sides times 1 minus y divided by negative y, and then you get times y prime equals 1. So it is separable. And it's autonomous. And I knew it was going to be separable because I saw that it was autonomous. The next equation, y double prime y prime plus sine of t equals 0. Is that first order or second order? Second order. Is it linear or nonlinear? This is nonlinear because of the y double prime times y prime. I can't even mix the primes, right? Or we call it nonlinear. Is it... Oh yeah, that's it. That's it for our classification. If I'm following that flowchart, I see it's second order nonlinear, and there's nothing else to do. We just give up. The next equation says y double prime plus ty prime plus y equals 1 over t squared plus 1. Is that going to be first order or second order? Second order. Is that going to be linear or non-linear? Linear. Is that going to be constant coefficients or non-constant coefficients? Non-constant, because of that t. That t is a non-constant coefficient. Is it homogeneous or non-homogeneous? Non-homogeneous, because 1 over t squared plus 1 is my non-homogeneous term there. If it was homogeneous, the right-hand side would be a 0. Two more. Y prime plus 2y equals 0. Is that first order, second order? First order. Is it linear or nonlinear? Linear. Is it separable or not separable? It's autonomous, so it has to be separable. Last one. First order or second order? Second order. Is it linear or nonlinear? Linear. Is it constant coefficients or non-constant coefficients? Constant coefficients. Is it homogeneous or non-homogeneous? Yeah, that 0 on the right-hand side tells me it's homogeneous. Okay.
Can we talk about the constant versus non-constant coefficients again?
Yeah.
That one's tricky.
Yeah, so like this one, since there is a t,
It's because it's a variable, right?
since we've got an independent variable t multiplying my y prime, that's a non-constant coefficient. Over here, I just have like -6 multiplying by the y, but -6 is a constant. There's no t's that appear here, so I say there's non-constant coefficients.
It's just because we don't know what t is. It's like because it's a variable.
Yeah, because it's
So
a variable.
R would have been. I don't think R was in this.
Well, if we say that lowercase r is just a constant, you know, it could be a constant. It's just saying that your independent variable, which is in this class most of the time going to be t, your independent variable can't show up among the coefficients. Yeah. So the next thing we're going to talk about is phase lines. Phase lines only apply to first order autonomous ODEs. That's the only situation that you would ever draw a phase line, is if you have a first order autonomous ODE. Otherwise, phase lines don't make any sense. But a phase line is a way to visually represent the qualitative behavior. An equilibrium point for a first order autonomous ODE is one where the first derivative is equal to 0. Because if the derivative is equal to 0, and this is a first order ODE, so we're not saying anything about the second derivative. If the first derivative is equal to 0, then the function is going to be constant for all values of t. An equilibrium point is called stable if all nearby initial points converge over time to the equilibrium point, but we say an equilibrium point is unstable if you can find a point nearby that diverges over time away from that equilibrium point. So exercise 5 says, for the following first order autonomous ODE, draw the phase line and label the equilibrium points as stable or unstable. So the first step, I think if you get this, y prime equals y to the 4th minus 4y squared, is going to be find equilibrium points. And an equilibrium point is where y prime is equal to 0. So I can write 0 is equal to y to the 4th minus 4y squared. Because that's what it looks like to set y prime equal to 0. And then how do I find the values of y that satisfy this equation? Yeah, I can factor out a y squared. How do I factor y squared minus 4? y plus 2, y minus 2. So y prime is equal to 0 at y equals negative 2, 0, and positive 2. And these are my equilibrium points. So when I go to draw my phase line, I need to mark where those equilibrium points are. At 0 and negative 2 and positive 2. And the only other thing I need to do when I go back to draw my phase line is I need to mark in between the equilibrium points which directions my solutions are going, okay? Like in between 0 and 2, we've got the number 1. If y is equal to 1, what does that say about y prime? Y prime would be 1 minus 4. So y prime is negative. And if y prime is negative, that means my solutions are moving to the left. Because in this region, y prime is less than 0. What if y is greater than 2? Like what if y is equal to 3? So I'm out here. If y is equal to 3, this is 3 to the 4th power minus 4 times 3 squared. So it's like 81 minus 36. That would mean that y prime is positive. And if y prime is positive, my solutions are going to be moving to the right when they exist out here. They're going to be growing if the derivative is positive. What happens if y is negative 1? So in here, if y is negative 1, this is 1 minus 4. It's negative 3. And so in this interval, where y is between negative 2 and 0, we have that y prime is less than 0, or y prime is negative. And then the last question we have to ask is about this interval from negative infinity up to negative 2. What if y is equal to negative 3? If y is negative 3, then this is 81 minus 36. So y prime is positive over here. And where y prime is positive, my solutions are going to be moving to the right. So now for my equilibrium points. Is this point stable or unstable? Stable. My equilibrium point at y equals negative 2, that is stable. Because all of the nearby points are moving toward the equilibrium point. What about this equilibrium point at y equals 0? Is that stable or unstable? Unstable. Because I can find some points like negative 0.001 that are close in the neighborhood of that point, but they're moving away. So we call it unstable. And then this equilibrium point, is that stable or unstable? Unstable. For the same reason. That's all you have to do. Draw the phase line, label the equilibrium points, stable or unstable. And remember, I can only do this for a first order autonomous ODE. Because in a first order autonomous ODE, the first derivative only depends on y. If it was not autonomous, then the first derivative depends on y and t, and I can't just represent the behavior with one number line. And if it was second order, well, then the second derivative is changing the value of the first derivative over time, and so it doesn't work either. This only works for first order autonomous. Okay. A direction field is a way to visually represent the qualitative behavior of a first order ODE. To draw a direction field, the first order ODE does not need to be autonomous. This is what you do if you have a first order ODE that's not autonomous. Let's draw this direction field. For the first order ODE, draw the direction field and the approximate trajectory starting. Okay. This is saying y prime is equal to ty. Here is my t-axis, and here's my y-axis. Y prime is, of course, dy dt, and dy dt is like the slope, the change in the vertical axis over the change in horizontal axis. And so that's t times y. Where t is 1 and y is 1, t times y is 1 times 1, so the slope is like positive 1, like this. If t is 2 and y is 2, my slope is positive 4, and so it's going to be a pretty steep slope there. And if t is 3 and y is 3, it's going to be positive 9. And just kind of, I mean, there's a lot of points you got to figure out, right? This is a grid of 49 different points, because it's a 7 by 7 grid. So I'm not going to explain every single one of these, but for example, if t is equal to 0, then the slope is 0. It doesn't matter what y is, right? Because it's 0 times anything is still 0. So everywhere where t is 0, I'm going to have a flat line segment, because my slope will be 0, so flat line segments. Anywhere y is 0, I also have a perfectly flat line segment, because t times 0 is 0, so the slope is 0 when y is equal to 0. When t is positive and y is negative, I'm going to get negative slopes. And when t is negative and y is positive, I'm also going to get negative slopes. When t is negative and y is negative, I'm going to get positive slopes again. And so it's definitely a lot of work to do this, right? To think about like 1 times 2 is 2, so I need a slope that's kind of steep. 1 times 3 is 3, so again, kind of steep. 3 times 2 is 6, that's very steep. But you can kind of, sometimes if you're familiar with the symmetry you're dealing with, you think, okay, 1 times 2, but it's negative. I'm looking for a negative 2 slope here and here, and a negative 3 slope here and here, and a negative 6 slope. It doesn't have to be exact. I'm not going to get out a ruler and figure out if that's a negative 5 or a negative 6 slope. But it needs to have the right shape to it, right? I'll be able to quickly tell whether it's positive or negative, or whether it's flat, or whether it's shallow, or whether it's steep. So try your best, but again, it does not have to be exact. Not by any means. Ta-da! There's my direction field for that ODE. Now in this problem, I forgot to give initial conditions. So I'll make up some initial conditions for you. Let's say the initial conditions are supposed to be this. t is equal to negative 1.5, y is equal to 0.5. So my initial condition would put me right here. If I want to give an approximate trajectory, I know that the slope is negative in this quadrant, but it never quite reaches 0 because the slope goes to 0 along the t-axis. And then when it crosses the y-axis, now all the slopes are positive again, right? And so it's going to start sloping up and up and up, and then it's going to get steeper and steeper. So this is an approximate trajectory. And there's some things I can say qualitatively by looking at this slope field. One thing I could say about the end behavior is that if my starting value is greater than 0, then y approaches positive infinity as time goes on. And I could tell you that if my initial y value is less than 0, then my y value is going to approach negative infinity as time goes on. So that's what your solution should look like to questions that look like exercise 6. For the following first order ODE, draw the direction field, an approximate starting trajectory starting from the initial conditions. Oh yeah, I guess you don't even need to say anything about the end behavior if the question doesn't ask you for end behaviors, right? You could also say if the starting y value is equal to 0, then y is equal to 0 for all t, for all times. Because if it starts right here and the slope is 0, it's got to stay 0 forever and ever and ever. Questions about that? I like to imagine these direction fields as like a current in a river. You guys been whitewater rafting? You should go whitewater rafting this summer. Imagine like here you are in the middle of the rapids and you don't have a paddle. So you're just sitting there in your kayak and like letting the water push you around. There's nothing you can do. Well, without any external force, without any paddling, this is the direction you would go. That's the direction the current would take you. Okay, last page of notes for today. A phase portrait. A phase portrait is a way to visually represent the qualitative behavior of an autonomous second-order ODE. So, for second-order ODEs in general, your second derivative would be a function of the first derivative and the value y and your independent variable t. But if it's an autonomous second-order ODE, that means that the independent variable t doesn't show up. So that way your second derivative is only a function of your value y and the first derivative, y prime. So I mislabeled this graph here because my axes should change now. My axes should have the horizontal axis be y, not t, and the vertical axis should be y prime. So the horizontal axis is now my y-axis. The vertical axis is now my y prime axis. And putting the direction lines down is going to be a little bit trickier. For one thing, I I need to just decide what my slope is going to be. Like slope in this context is going to be the derivative of y prime with respect to y. That's kind of weird. How am I going to find that value? What we're going to do is say this is the derivative of y prime with respect to t divided by the derivative of y with respect to t. Does everybody agree that would actually be the same thing? Because you could multiply by dt in the numerator and denominator and cancel out those dt's. Okay. Well, what's the derivative of y prime with respect to t? It's a derivative of a derivative. So that's the second derivative. Y double prime. And what's dy dt? That's just y prime. And so the slopes of the little line segments I'm going to put down on this plot are going to be what I get for y double prime divided by what I get for y prime. When I look at this differential equation, I can rearrange this to say that y double prime is going to be negative y. So here in the numerator, I can just write negative y. And I'll get that the slope at each point is going to be negative y divided by y prime. I don't need to do anything more because y and y prime are the coordinates of my plane right here, of my grid. So everywhere where y is 0, I'm going to have a 0 slope. So where y is 0, boom, 0 slopes, flat line segments. Everywhere where y is positive and y prime is positive, like in the first quadrant, I'm going to have a negative slope. In fact, I'll have a slope of negative 1 where they're equal. And in fact, when y is negative and y prime is negative, I'll also get negative slopes down here in the third quadrant. Where y is negative and y prime is positive, two negatives make a positive, so I'll get positive slopes here in the second quadrant. And where they're both, or sorry, where y is positive and y prime is negative, two negatives make a positive here, and I get positive slopes there. If y is greater than y prime, I'm going to get more steep slopes. So like that should be a pretty steep slope. And these should be pretty steep. If y prime is larger than y in absolute value, I'm going to get pretty shallow slopes. And so that's going to be pretty shallow here, here, and here. Oops, let's go in the wrong direction. Shallow positive. There is a sense in which it makes sense to say, well, since along, I use the word since a lot, along this y-axis, I've got a number in the numerator and a 0 in the denominator. It's going to make sense for us in those situations to put a vertical line. And then where I have a 0 in the numerator and a 0 in the denominator, 0 divided by 0 is an indeterminate form. So that is the right way to make a direction field, or a phase portrait, I should say phase portrait, for a second order autonomous ODE. There's one thing that's kind of still missing from my picture though, and because time is not an axis, I don't know which way time is going, right? Each of these line segments is not directed yet. I should put a little arrowhead on each line segment so I know the direction that the line segment is going as t is increasing. How do I figure out the direction that each line segment is pointing? Like, is this line segment pointing up or down? Is this line segment pointing left or right? It's a good question. What we need to do is look at y prime. If y prime is positive, that's saying the change in y over time is positive. So in the top half of the plane, where y prime is positive, the change in y over time should be positive. Y is the horizontal axis. And so as time moves forward, y should be increasing when y prime is positive, right? So I'm going to add little arrowheads that show everything moving to the right when y prime is positive. Oop, got ahead of myself. And then on the bottom half of the plane, y prime is negative, so the change in y over time is negative. And so over time, the horizontal values should be moving to the left. And so I'm going to put little arrowheads that show everything moving to the left over time when y prime is negative on the bottom half of the plane. And then based on continuity, we should kind of intuitively see what direction the arrows should be going there. So, given these initial conditions, and I like to use m with a subscript 0 as the initial value of y prime. I'll try to keep that convention the same throughout the rest of the semester. So where you see y naught comma m naught, I'm talking about having a 1 for my initial y value and a 0 for my initial y prime value. And so this is my initial condition. And the question is asking, what would an approximate trajectory look like starting from here? Well, I'm initially going down, and then things seem to be swirling clockwise. Like that. That's my best guess at an approximate trajectory. So that's a lot of steps. It's a lot of work, but that's how you'd answer a question like exercise 7 on your homework.